Summarize what we did last time. So what we talked about where the renormalization group is useful, and the answer was in critical phenomena, particularly because the crucial point is that there are a large number of degrees of freedom involved, and at all scales there's correlations. So the correlation length was an important quantity. So I'll just write it here. When this is large, that is where the renormalization group helps. Okay, so that's the first point. And the second thing I mentioned was what is the procedure involved, what does the renormalization group do? So the idea set out by Kadanoff and Wilson and so on is that you start with your original Hamiltonian, which by the way has to be local. We are assuming that physics is local, nature is local. Local means every degree of freedom interacts with the degrees of freedom which are right next to it, not far away. Okay? So you start with a Hamiltonian that's local, then you do a transformation to a new Hamiltonian that involves some kind of an averaging over a small region. So if you're talking about spins, you take a small region around the first spin, which may include the nearest neighbors, and take an average of that and describe new degree of freedom for that average. So effectively you replace a few spins by, let's say, one spin. So that reduces the number of degrees of freedom, and in terms of the new degrees of freedom, you obtain a new Hamiltonian, which is again local on the new length scale. So this transformation is called blocking. Okay, so you can do it in real space, or you can do it in momentum space, and we're going to do that today. Once you do that, so you start from one Hamiltonian, you get another Hamiltonian, which is related to the old one just by this. Essentially a factor of 2 scaling, which is because you've averaged over some region. And this transformation hopefully is quite simple. Okay? And then you iterate this a large number of times. And you end up with a final Hamiltonian. And the final Hamiltonian will have the distance between nearest neighbors will be of order the correlation length. So the idea is each time you do this blocking, the distance between 2 points increases, let's say, by a factor of 2, and you keep doing it till you reach the correlation length. At that point, you have a Hamiltonian, and there are no correlations on a larger scale, so it becomes like a hydrodynamic problem. You can just write down equations of motion and study that problem. Okay? And then we said that the crucial thing here is the map from one Hamiltonian to the next. The importance lies in that map, and then you can study the fixed points of that map and so on. So today what I want to do is to do 2 things. One is to describe the intuitive idea of Kadanoff, which is implementing this, and we'll see how you get out the kind of behavior you expect at a critical point where things are singular. And then we'll apply it to the simplest model, which is called the Gaussian model. Okay? So that's basically free field theory. So let me talk about Kadanoff's idea of blocking. And just for reference, I'll define some of these terms. So the model we're going to talk about basically is a spin model, Ising model. So I'll write it like this: sum over all spins. So this is the partition function. So I think there's some confusion about the sign. So what this does is it favors that the 2 spins should be aligned, because then this is a positive number, so the contribution to the partition function is large. If the spins are opposite, it will contribute less to the partition function. Okay? So you can think of this as involving the Hamiltonian, which is minus j times sum over n, sum over I, Sn. And then the partition function is just okay. So J by KT is that K. Okay, that's the first point I want to make. The second thing is, since I've talked about this correlation, let me just define what that means. So we define gamma n like this. It's the correlation between the spin at site 0 and the spin at site n, e to the power of h by kt divided by okay. So this is just normalizing it with the partition function, and this is the correlation gamma n.
The Hamiltonian is not nearest neighbor interaction.
Here it is. N and n plus I, which is in the various directions. So if it's a two-dimensional model, it'll be
I is the direction.
yeah. I should have said that. So this would be, so if you have spins like this will be coupled to this guy, this guy, this guy, and this guy.
A unit vector.
Yeah. Yeah, I should have said that. Thanks. So this is the 2-point function. And typically, this will fall off as e to the power of minus n. Okay? Or actually, maybe I should use the word x. I think no, n is. So this is n. N is in units of the lattice length. So n is the number of lattice sites. So distance in units is the lattice length, and this is some number. So at this point, these are just numbers. The length unit is the nearest neighbor spacing, the spacing between. So you can call this length some L naught or A or anything, but that doesn't matter. It's a ratio. So this defines what I mean by C. I keep talking about correlation length. That's this thing. The other thing is, at the critical point, this diverges, critical temperature, and then this goes as some power of the distance, and okay, it goes to some power, and this is some this is some definition. So this defines an index, something like which measures basically the dimension of the operator of the object, and so it's a power law. The power is not an integer. This is an integer. This is a non-integer part of that. So this is just some basic things. And then when we talk about things like magnetization, you're talking about expectation values of Sn at one point. So if you want. And then you average over the sites. And of course, you divide by the partition function. So what you're doing, you're calculating the expectation value of a spin at a site n, sum over all n and divide by capital N, which is the total number of spins. That's the average. And this is, of course, just the normalization. So this is what we mean by magnetization. So those are just some basic definitions. So now I'll talk about the blocking, the idea of blocking as Kadanoff. So yesterday, last class, we talked about mean field theory, and we got out some critical exponents and so on, working with this object. So what does Kadanoff have to say? So Kadanoff's idea is the intuitive idea, which is going to be made precise when we do the RG. So his idea was, let's start with some spins. So you have a lattice of spins like that. And what he said was, let's consider a block like that and take some average of this. You have to have some averaging procedure. Replace this block by one spin. Okay? So you can have different rules how you do that. So you can say, if you add up all these spins and if the net spin is positive, you call the spin as +1. And if the net spin is negative, you call it as -1. So that's one scheme. So basically, So of course, if this spin is 1, 1, 1, 1, and you add it, it becomes 4, whereas here it's 1. So you've done a normalization. That's not very important, but so the model redefines these 4 spins and puts 1 spin in its place, which again we normalize to take +1 and -1, and you can have some scheme for deciding when it's +1. You say if the average, the sum is positive, you +1. If the sum is negative, you put -1. Something like that. And then you replace this also by the same kind of thing. And now you have this thing replaced by 1 spin and this thing replaced by 1 spin, and you see the distance between these two is twice what the original thing was. So if this was L0, the distance between these two is now 2L0. Okay? So in your new Hamiltonian, you will have a spin here, a spin there, separated by L0, and so on for the rest of the lattice. So you've done, this is called blocking. Now you can ask what's going to happen to this K, and so you look at the energies and you say, so you consider the bond, this two, consider these two. So if you're basically saying these two spins are up, this has an energy K, and if these are up, this has an energy K. So in this new model, it's K plus K, because if this spin is up and this spin is up, you should get 2K. So roughly speaking, you would replace K by 2K. So in this scheme, you will replace an iteration K prime, you can imagine will be twice, because the interaction between these two, there are 2 spins with nearest neighbor interactions, and so it's 2K. We'll, of course, modify this later on, but let's start with this assumption. So you get a new Hamiltonian where the spins are averaged like this. The distance is 2L0, and K has become K prime, which is 2K. Okay?
These blocks have to be non-overlap.
Yeah. Yes. In this simple scheme. So just looking ahead, later on we can do this in momentum space, but then this geometric picture will be not directly applicable. But here we are just doing a simple-minded thing. Okay, so now one thing you should realize, as soon as you say it's 2L0, or I call it A here, you can call it 2A. If suppose the correlation length in the original theory was, let's say, 1000 lattice spacing, so let's say it was 1000 L0. Okay, in your new, so this is a number that's relevant. It's 1000 times the lattice spacing. In the new scheme, your correlation length will be 500. Why? Because the length is 2L0. Okay? So your correlation length in the new theory is now 500. Where when you say 500, it means 500 times the basic length, which is the distance between the spins. So your correlation length has become half, and your K prime has become double. So in this simple scheme, that's all that happens. So let's see what are the consequences of this. So I'll call this is one iteration, so I'll call this K1. So you have a relation that C of K1 is half right, and if you call this F of K, so this is F of K. Okay, now at the critical point, so suppose you're at the critical point, then K1 is just Kc. That's the critical point. So that means C of K1 is infinite, because that's C of Kc. Right at the critical point, C is infinite. That means this C is also infinite. Right? So you infinity. But then if this is infinite, this must also be Kc. Okay. So you get a funny thing that says K1, which is 2K, is Kc, but K is also Kc. So you see that 2Kc is the same as Kc. So this implies so there are only two possibilities, Kc equals 0 or Kc equals infinity in this simple scheme. So I hope you see the logic of what we're going to do. We're going to modify this in a minute. So because your correlation length is infinite, essentially nothing is happening. Okay? So basically that means you've reached a critical K. But then this relation cannot be true. I mean, if it is true, then Kc has to be 0 or infinite. It's sort of trivial. So what Kadanoff did was to modify this. He said, let's not use this simple 2. Let's just say K1 is f of k. So this is not acceptable. So this is extremely simple-minded, not acceptable. Let's modify it. So you say, so your new K1 is some f of k. Don't assume it's 2k. It's some f of k. Okay? But you make the assumption, which is very crucial, assume that it's analytic. Why are you assuming it's analytic? I emphasized this in the last class because until you hit k equals kc, you don't want things to diverge because you're always talking about finite number of degrees of freedom. Why? Because this blocking scheme involves only a few spins. It doesn't see the whole Hamiltonian. It's just some operation done locally. Just a few spins are involved in this blocking. So you should not expect any infinity due to the thermodynamic limit or anything. So this must be an analytic relation. Okay? So that itself is quite powerful. It takes you a large distance. So then, so you modify this to that, and then this gets, what does this become? C of f of k is half of, right? The factor half is the same as before because you block 2 spins to 1. So that's why it becomes half. The new thing is this f of k is not 2k, it's something else. So we assume some form of f of k, do a Taylor expansion. This is f of kc because it's analytic. And you say it's some lambda times k minus kc. So if you're near enough, you could just do that. Okay? Then we know that c has to diverge at kc, so let's assume that it has some divergence of the form ck. Let's assume it has the form k minus kc to the power of. So this is an assumption. So we'll try to determine this nu. Why are we making this assumption? Because we know that at kc it has to be infinite. Kc is by definition the critical point. So it should go to infinity, and we'll assume that it goes to infinity like that. So we'll substitute this, see what you get. So you get c of fk by c of k is fk minus fkc minus kc by fkc is that. Okay. Now if you use this, fk minus fkc is just that, and k minus kc cancels. So this is basically lambda to the power of minus nu. Okay. what is this ratio? Half, because you just done one blocking. So this is half. So you can calculate nu from this relation. So nu is just log 2 divided by log lambda. Okay. So what have we achieved? We've achieved one of the things that we did in mean field, which was to show that you get non-analyticity at Kc. And we find that the non-analyticity is governed by this exponent, which is a function of this blocking scheme. And here it just involves that parameter lambda. Okay. So what Karanov was looking for, he found that critical exponents can be obtained this way. What's more, it's not some simple mean field values generically. It depends on this lambda. Okay. So the idea that critical exponents could be different from mean field values, which the mean field value is what we did last time. I think this was probably the first time he was able to obtain it from a theoretical picture. Okay, this blocking scheme. Okay, and of course you can now iterate this. So this gives you the non-analyticity. Now how do you use this? Let's just, yeah. Oh, why is this half?
No, not half. I don't know.
No, I assumed that C of k has what did I assume that C of k has this form, and I assume that F of k has this form. C of Fk, so you put Fk here. Huh?
Fk minus Fkc by k minus kc.
F
minus nu.
Fkc is just kc, yeah. This whole thing. Right, yeah. So this is Fk minus Fkc is just kc because it's a fixed point. So Fk minus Fkc by k minus kc to the power of minus nu. So this is just lambda. What was I going to say? Yeah, so you got the non-analyticity. Now in practice, so the next question is how do you use this technique? Now you've got the critical behavior, but how can you use it in practice? How do you use this in practice? It's just a strategy which is used all the time. How to use this in practice? So this is a question of how do you use RG in general, and the idea is that when you do this blocking, your k changes quite a bit. Okay, so the k before blocking and k after blocking are very different. Okay, so you can relate k that is very near kc to k that is far from kc by this scheme of blocking. So if you have k, let's say, much greater than kc, you can do a blocking and relate to k near kc by so in your Hamiltonian there's a parameter k, and the parameter changes. It's the same form of the Hamiltonian, but the parameter changes as you do this blocking. So the value of the parameter changes with each step. So you can go from some value k near kc to some value, much bigger, let's say, than kc to some value k near kc by a blocking transformation. So these two can be related. Okay, and c. So if this is your initial k and this is your final k, c initial and c final are related by some power. So if you do it n blockings, it's like that. Okay, so if your final k is if your initial k is, well, how does it depends on which way you're going. So each time you block, your C halves. So if you do n steps, you half n times. So if you're able to calculate, so the idea of this renormalization group is you're able to calculate with the Hamiltonian where C is very small. Okay? C is small. C is large is very hard to calculate. That's the region where you have large correlation, long distance correlations. C is small is easy to calculate. So if you can calculate, so maybe I should interchange this. So if I can calculate with this guy, okay, suppose I can calculate with this guy where C is small, okay, then I can, the RG relates this theory to this theory where C is large. So and I can get the K, or I can get all properties with this K by calculating with this K, because everything is, there's a map. Okay? So the idea is you do your calculation in a region where you can, which is where the correlation length is small, do your calculations, and then by this, the RG tells you the relation between the parameters, the quantities you calculate in this regime and the parameters in the regime where it's hard to calculate. And you just do that mapping. And this is exactly what is, how RG is used even in perturbative, for instance, in QCD and field theory and all that, where you calculate in some regime where you trust your calculation, use the RG to evolve it to a region where you can't, those techniques don't work. Yeah.
When you write down this K prime, K1 equal to f of K.
Yes.
F of K is some function which depends upon your RG.
Depends on the scheme. Yes. Yes.
But then this lambda is a function.
So lambda depends on the scheme. Yes.
So that mu will depend upon the scheme.
So ideally, at this point it seems to depend on the scheme, but in an actual calculation you will find that it doesn't actually depend on the scheme. It's a property.
Function you take, it should come out.
Yeah. No, well, you can't choose whatever function you want, but there will be, depending on what your scheme is, you'll get some function, and that scheme will automatically lead you to some nu. And if you've done your calculations correctly, because the nu is a physical quantity, your nu should not depend on the details of the scheme. So if you do it in two different schemes, two different blocking schemes, you should get the same nu. So that's the statement about, well, that's a test of whether the blocking you've done is, the scheme captures all the information or not. Okay. In fact, so we'll do a specific calculation with the S4 model, and you'll see that it doesn't depend on the scheme. So here in this scheme, the blocking, for instance, just the only detail is this factor of 2. I mean, I could have taken a region of, say, 9 spins and done the blocking. Then it would have been 3. Everything would have been 3, and then this would have been log 3. And ideally, this should change in such a way that this ratio comes out the same. So your lambda will be different. Okay? So here the scheme dependence is one scheme dependence is a factor of 2, but it doesn't have to be a factor of 2. Could have been a factor of 1.5 or 3 or any number greater than 1. So those things should not affect the value of nu. Okay, so this is the intuitive idea of Kadanoff, that his blocking and how he got out critical exponents and showed that you can get things different from the mean field value in a simple way. So what we're going to do now is to apply the scheme to the simplest model, which is the Gaussian model, where Hamiltonian is something like that, and go through all the details of the renormalization scheme, because this is physically it's a fairly trivial model, so you can see what's happening. We will later on complicate this by adding interacting terms which are quartic in S, but then you realize that all that's happening is that whatever happened here is corrected by small amounts that depend on the perturbation that you added. So the details of this, all the conceptual things will be seen in this model. Okay? So I'm going to study the blocking of this model in some detail. Okay? Any questions about this?
Can you say a little bit about this assumption?
Analyticity. So the analyticity assumption is crucial. The reason you make that assumption is because when you do field theory,
No, I mean the assumption that the psi goes like a power down.
oh, no, because you want some diverges.
So the only way it can diverge or some physical input is going on.
Well, physical input is experimentally that's how things go. So it's some divergence, but you don't know. But presumably this is fairly general. I mean, what could be more general than this? You could have a log, other than that. Pretty general, because nu is an irreal number. And as I said, the analyticity is because your blocking involves only a few spins at a time. So there's no reason for anything to become non-analytic. That's the crucial part of the RG. At each stage, only a few degrees of freedom are involved. So let's do it for this model. So I will erase. And we're going to work in momentum space.
Well, exponential 1 over k minus k.
Ah, yeah, well,
If you want me to think about it.
right. So I will erase all this. Oh, maybe I'll erase it when I get there. Okay, so now we're going to do okay, now first step, okay, we're going to, this is the Ising model where S takes the value +1, -1. We're going to, whenever you have some discrete things like that, that's very hard to treat. So it's actually fairly complicated because of the discrete nature. So we're going to approximate it, modify the model in a very brutal way and simplify it to get the Gaussian model. And later on, we'll see how we make it less brutal. Introduce continuous variables. See, discrete variables are hard to deal with. You can't use calculus. So you introduce continuous variables. And so this is actually, what I'm going to do is a lot of cheating. So at this point, I haven't done anything. So yes, so Sanatan reminded me, these are unit vectors in the various directions. So I've just imposed this as a constraint. So Sm squared is 1, so Sm is +1 or -1. Okay, that's the first step. So Sm is now a continuous variable. Yeah.
What are these final names to compute the
Critical exponents and various other correlation functions, specific heats, various things. Well, in field theory, you would be interested also in S matrices and things like that. So this is the first step. That's a trivial first step. Now, so here you have the function is, so if this is 0, it's either over there -1 or 1. Everywhere else, there's no other possibility. So the first step is to relax this and spread it out like that. And then we'll relax it even more and spread it out like that. Okay, so this, you might think bears no resemblance to the original one, but this is the so-called Gaussian model. But actually, so let me, so here you replace this delta function by something like e to the power of -12 b Sm squared. Okay. So here Sm was either 1 or -1. Here it's peaked around 0, but it can take all values. So so instead of taking value here and here it's spread out. And the average is still 0, but it's peaked at 0. Here there's no, 0 is not allowed. Okay? So it's not the same model. but we modified it. But you know, you can modify this model later on by adding something like this with some sign. This can be further modified to this, and in some limit where b and u become large, you can reproduce a delta function using this. Okay? So if b goes to infinity, u goes to infinity, you can tune it so that this becomes a delta function. Okay? So if you want, you can say, you can start with this, write this, say that this limit, this is equal to that, and then say I'm going to relax this limit, make b and u finite, and then go further and say I'm going to put u equal to 0. So that's how you go from the Ising model to the Gaussian model, to these stages. And for the first, so beginning we're going to study this model. So we'll just
Sm squared and
SM4, yeah.
when you have Sm4, it looks like the first one, right?
Ah, that's what I'm saying. So in the limit, when this is large and this is large, this becomes a delta function in Sm squared. So it becomes exactly that. So for finite,
you will ignore Sm4.
Yeah. So you can replace. So as I said, you can replace this by this with b infinity, u infinity, and tune to get 1. And then we'll let b and u be finite, and then we'll let u be 0. So by this sequence of steps, you distort the model and make it this. This is called the Gaussian model, which makes it very easy analytically. Okay. So of course, one of the reasons, now this model is also very different, even with u finite. This is very different from the Ising model, but very often you can appeal to some universality arguments to say that the critical behavior of different models are the same. Remember we said universality means that the parameters of the original Hamiltonian don't matter too much. So you might hope, you can hope that this model with u finite, p finite is in the same universality class as the Ising model. So some things, even though it's a different model, you can learn a lot from this model. But for our purposes, I'm doing this mainly to illustrate the RG steps. Okay? So the Ising model, the connection with the Ising model is really a motivation. It's not, I'm interested in this model and then this model. So let's stick with this model. So let me erase this. So now my model is the following. Your Hamiltonian is k sigma ni Sn is n plus I minus half b sigma n is n squared. Okay? Or actually I should say, let me call it this S, whatever action, I've called it S. So I'll complete the square and write it like this, minus half k sum over ni Sn plus I minus Sn squared. So the cross term here is this term, and then you have to subtract some squares to make it equal to that, and what you subtract is this. This d is the dimensionality of your lattice. So if you're in 2 dimensions, d is 2. This k is that k. Okay. So this is the first step. Next step, so this is 1. Next step, go to momentum space. So we'll do a Fourier transform. Okay. So we'll define sigma q as sum over n e to the power of I qn. For some reason, Wilson puts a minus sign. It's not important. Sn. That's his definition. Okay. And if you put this into that, what you get is very easy to see. This is n plus I, this is n, so you'll get a qn and a qn plus I. Okay? So you get you're familiar with this from what you do in solid state physics, plus r tilde. This whole thing multiplies sigma q, sigma minus q. This is that, and this is that. Okay? So r tilde is all this. Is this clear? So unless there's a factor of half, yeah, this is right. So this is this. That's the second step. Third step, by the way, you notice that there is no, this is Q, well, it's actually QI. Sum over I in the I direction. Okay, so it's Qx, Qi, Qz. Okay? Notice that there is no length here. Usually you have e to the power I kx. The reason there is no length here because everything is being measured in units of the lattice spacing. So lengths are measured in units of the lattice spacing. Q is measured in units inverse lattice spacing. So Q actually goes for a range of minus pi to pi. Okay? Each of the Qi, Qx, Qi, Qz actually have this range. Remember the momentum on when you have a lattice spacing A, the highest momentum you can get is 2 pi by A. Okay? So, so minus pi to pi, that's the range of Q. So it's a number. The scales have all dropped out. So when you say Q is small, what you mean is Q is small compared to pi. That's a number. And actually we will simplify this and by this range of integration is d dq by 2 pi to the power of d. That's what this means. Where Q is this range. Each of the Q's are in that range, minus pi to pi. Okay? So I should write each one goes from minus pi to pi.
Why we are assuming Q is small?
To simplify. Just to simplify the problem.
That exponential will become something.
That's right, yeah. And I'm going to make a further simplification, which is, again, just to simplify the algebra. Instead of going, so the magnitude of Q goes from 0 to pi. I'm going to assume the magnitude goes from 0 to 1. Just to simplify. All these things are not very essential. I mean, you can put back the pi's and all that. But just to make life simple, we just say, if you want, you can think of this as redefining your Q. But let's just say 0 is less than Q is less than 1. Just a simplifying assumption. There's no physics in this. Just to keep the calculations and algebra simple. Because we're going to make a lot of simplifying assumptions to simplify the algebra. The final results don't really depend on all those details. So Q is small means what? Q is small means you are interested in correlations that are long distance correlations. Correlations that are much larger than a lattice spacing. So if your lattice spacing is A, you're interested, let's say, in 100A or 200A, things of that range. So you can afford to make Q small. Okay? So this means Q small compared, or so I should say wavelengths much larger than lattice spacing. Or in field theory language, you're interested in the low energy behavior of the theory, long distance behavior of the theory. So let's simplify it. So when you simplify it, what happens? This becomes minus half becomes something like this. This is something you recognize. It's just what we call free field theory. Okay? Where R is basically, so I've changed my units. There's a K. What happened to the K? This K. So this K times R tilde is R. And so the K will multiply the sigma, and I've also chosen the normalization of sigma so that K is 1. Okay, so sigma is normalized. So this is all simplifications of your starting Hamiltonian. Get rid of as many of the parameters by rescaling and so on. So anyway, these are variables that you're going to integrate over. So you're free to choose the scale. We'll choose it so that this K is 1. So you're starting with this. So this is our starting theory, where this Q is now in this range. Okay? And R is basically R tilde times K, where R tilde is all that. Okay? Okay, so now we're going to work with this theory. So let me erase this now. Now we can define things like correlation length in this theory. So let me do that, because at the end of the day, that's what you're going to calculate, the correlation. So what is the correlation length? So let's first define. So now we've gone from a lattice to a Q, momentum space. Once you've gone to a Q, you can define a continuous X by taking the dual of that. So define S of X as again, this is just a definition. Okay? So this X has some loose resemblance to the original length. Originally it was discrete set of points now, but this X is continuous. So it's like somehow you approximated that discrete lattice by a continuous variable X. But you have to worry about all those rescalings. But anyway, this is your S of X. Okay? And you can define, in terms of this, correlations. Okay? And so this will be defined as integral over sigma S of X, S of 0, e to the power of minus half, sigma Q, sigma minus Q, Q squared plus R by Z. So this is my definition of the 2-point correlation. And this will be, okay, let's do it in momentum space. So if you do this, what will you get? You can easily show that this is basically going to be, you won't be surprised to see this. You recognize this. This is, when people who've done field theory recognize this as basically the propagator for the sigma field. Okay? But you can do this calculation explicitly, and this is what you'll get. This is basically a Gaussian integration. So the expectation value of 2 S's is like expectation value of 2 sigmas, which is going to go like 1 over that. Okay? So Gaussian integral, so you'll get this. So this has a singularity when Q squared is minus R. So Q is basically I times square root of R. So you can see how this will fall off as e to the power of minus x times square root of R. That's how this is going to behave. And then you can read off the Is this point clear? So this R that we got in this, which is all this to some scale, is basically giving you the correlation length. Sorry, which summation? Here. Yes, this is a Fourier transform. This is the Fourier transform of sigma.
Inverse of this will involve an integral. It's just that the variable would have been the side plate. You're just making it into a continuous variable.
This is,
Approximation as far as some.
you can work with sigma q if you want. Okay, you can say sigma q, sigma minus q correlation, and you'll get the same thing. In momentum, in position space, that's this. This is the Fourier transform of that. Okay. So this is just, if you undo this thing, you will get that. Okay. So C is 1 over root R. Now again, for people who are familiar, in field theory, this R plays the role of mass squared. Okay, so mass squared, and this is saying the correlation goes as 1 over mass, which is what you expect. And a Yukawa potential, let's say Yukawa potential, the things drop off as 1 over the mass of the particle that's exchanged. So this is just that. So you should think of R as mass squared in a field theory language. Okay? But here, what is the significance of R? R is this quantity. The precise value of R is R tilde by K. So, oh wait, this should have been R. Well, okay, I'll write down the precise units later on. R is R tilde by K. So this R, yeah, I think it should be R. This should be R. This K doesn't multiply that. So this is Rk. I've taken the K out, separated out the K. So K times whatever was there is what I'm calling R tilde. Okay. K doesn't multiply the R tilde there. So the parameter that plays the role of mass squared in a field theory is played by this R in this critical phenomena theory, where R is basically this. Okay? So you can ask what means when R goes to 0. So in a field theory, when the mass goes to 0, you get a massless theory with infinite correlation length, power law fall off. Here that happens for some critical value of K, where this is 0. Okay? So the critical value is Kc is when this is 0, so it's B by 2D. Okay? So at K equals that value, this becomes 0, and you have your critical behavior. In a field theory, that corresponds to saying the particle is massless, the field is massless. Okay, so I've just defined for you the model. So let me define a couple of more things, just so I think I can erase this now. So what we have to do now is to do the RG on this model. As of now, all I've done is taken my Ising model, modified it, put it into momentum space, changed the range of momenta, and simplified it to low momenta, and got this model. Okay? So we will define correlation lengths or 2-point functions of this type. So let's say sigma, so let me write this, sigma q1, sigma q2 integral over sigma e to the power of minus half q squared plus r squared, r sigma q sigma minus q divided by z. This we will define as what? I don't have a definition. I will define this as gamma of q1 delta of q1 plus q2, where this is the d-dimensional delta function. Why is there a delta function? That comes from translational invariance. So this is what we define as gamma q. Okay? It's for later reference. So in this definition, this object is actually, so when I calculate this, what I get is delta, well, if I call this q1 and q2, I'll delta get q1 plus q2 by q1 squared plus r. So this is the, so our gamma of q1 in our example is this 1 over q squared plus r. Okay? So this is just I'm just defining 2-point function in momentum space, taking out the momentum conserving delta function. So it's just this functional thing, 1 by q squared plus r. So in this case, it's very simple, but it's useful to have a general definition which you can use in more general cases. And again, now here the correlation length was very simple because it's just the value of this, 1 over that. But more generally, you can define it as the inverse basically of the singularity point of q, wherever q becomes singular. And it's useful to define it this way. So you can define q squared as, so you think of expanding for small q, expanding this in powers of q squared. And the first term that's constant, that defines the correlation length. So this you can write as d gamma by dq squared. So this whole thing, this ratio. So in this case, d gamma by dq squared will just, if you work it out, you will just get 1 over r for the simple example. Okay. What else can I say? And then I can say that this is also, if you work this in position space, this is just derivative with respect to q squared is like 2x squareds. So it's x squared times gamma of x times d dx by so this is like the second moment of x, expectation value of x squared in this correlation. So that's the intuitive meaning of the correlation. So there's just various ways of defining this c squared. Okay. But probably the simplest ways to think of is just this. It's the rate at which the exponential falls off. Okay, so now we're going to do RG on this model. Let me ask if there are any questions on the model itself or the transformations. So we have a model, we know what c squared is, and we know how to calculate c. Now we'll do RG and see how things go. By the way, I need to know the time. I'll stop at 12:30. Oh, so maybe I should. I'll stop in a few minutes. I'll just outline the steps and then continue it next time. So I'll just outline the steps. I won't do it because I don't want to do it in a hurry. So the first step will be we have to do the blocking how are you going to do the blocking here? Because we're in momentum space. The way you're going to do it is integrate all sigma q's with q greater than half. So we are in this range because upper limit for q is 1, lower limit is 0. So integrate out everything greater than half. All the sigma q's with q greater than half. Integrate it out. So what does that do? It removes the high momentum components of the sigma, which means the wavelength. So if this is your lattice, so this is your lattice spacing. If you, high momentum component would have oscillations like that, and you don't want those. Okay? So another way of saying it is, I want to, if I have this thing and I want to replace it by a lattice like that, I don't want wavelengths which are smaller than this. I only want wavelengths of that size. So you get rid of the half the wavelengths, integrate out sigma q's. Okay? Second step is to rescale all quantities. What's the criterion for rescaling? You want to make your final Hamiltonian and functional integral look exactly the same as the original one, except the parameter should be changed so that h and the functional integral z look the same except for change of parameters. So in our case, the only parameter is r. In this trivial example, r is the only parameter. So what does that mean? You should, whatever you do at the end of the day, where is my s? It should look like what? It should look like this. It should look exactly like this. And you see here the range of q is from 0 to 1, right? So it should look exactly like this with the same thing, except this can be different. That's the thing. So whatever rescaling is required for that, you do. And then find r prime as a function of r. That's your transformation. Second step. No, so after when you do this integration, your Hamiltonian will look different because first of all the range will be different, so on, right? So you have to do some rescaling of your variables, whatever the variables are in your theory, in such a way that the final Hamiltonian has exactly the same form, which means everything should be the same range of integration, the form should be of this type, q squared, and only change is the parameter can be different. So it should be a Hamiltonian in the same form but with a different parameter. And your aim will be to find the new parameter as a function of the old parameter. That's what you have to find. And then you're done. Then that's your RG transformation. Then extract the physics from that, that's all. Okay? So this is, okay, this I don't want to hurry through this, so I'll stop here and do that on Tuesday. If there are any questions, this is good. So I hope it's clear what we've done. We started with an Ising model, simplified it a lot, made it into this so-called Gaussian model. This is the Gaussian model, which in field theory is just a free field theory. And for this model, correlation length is known. It's 1 over root r. And now we're going to do an RG transformation on this model and see what happens, to, how you get the. Step 1, what is step 1? So here you're doing a functional integral over all the sigma q's. So there's sigma 0 to, so you have sigma q's, the q ranges from 0 to 1. So the sigma with q greater than half correspond to wavelengths which are smaller than your new lattice spacing. Your lattice spacing is 2 times the old lattice spacing. So if you have momenta which are roughly half the higher half of the momenta correspond to wavelengths which are smaller than your lattice spacing. But you want to average those out. You want to get rid of those. You don't want variation smaller on a scale smaller than your new lattice spacing. So that means you get rid of the sigma q's with q larger than a certain amount. Since it's just scaled by a factor of 2, that point is half. So you get rid of all the q's with q. So this corresponds to blocking where you double your length scale. If you choose this to be 1 by 3, that would mean 3 times and so on. Any other questions?
We are able to solve that problem exactly.
Yes, yes.
Why still we are doing algebra?
To illustrate the steps involved. We illustrate the steps involved in all this because when we add the S4th term, the steps involved will be the same. Only the actual details will be modified. Everything else will be the same.
Just a practice.
Yeah, but it introduces all the concepts. Okay, so we'll stop there.